Hello everyone, welcome back to my channel. Do you like music? Music makes the people come together, makes the bourgeois and the rebel, and it makes also the MSX. In this video we'll be seeing how the audio signals, which are generated by the MSX engine on the other side of the board, look like on the oscilloscope, and how this little hybrid board is able to amplify, filter and control them. Let's go for it! Well, after listening to this excellent music, let's see how this works. There are four sources of audio in this MSX. You have the PSG, you have the PPI, and you have the two cartridges, cart 1 and cart 2. The PSG is the main audio chip in this MSX. It is the programmable sound generator. And in this MSX in particular, it is integrated inside the MSX engine. In other systems, it is a separate chip. Another source of audio in this MSX is the PPI, the Programmable Peripheral Interface, which is responsible, among many other things, of generating the click sound that you hear each time you press a key, in BASIC for example. And finally, the sound might come also from any cartridge that you put at any of the two slots. The cartridges can generate sound and inject it directly into the motherboard using this pin 49 sound in. These four sources of sound go to this board, the IC hybrid board, where they are mixed, amplified and filtered. Here you can see the audio inputs to the board, the PSG, the PPI, and the two cartridges. The first thing that happens to each of these audio signals is that each of them go through a decoupling capacitor and then they are mixed together. After being decoupled, you can see that all of them go to the same point, so they are mixed together and then they are amplified and filtered by this part of the circuit. For the inverting input, if we follow the trace, we see that it is connected to the mixed signal. And if we follow the non-inverting input, we see that it is connected to a ground. So we can put a ground symbol in here and try to compute which is the tension that we have in here. So we have 5 volts, but we can call it V in, these 5 volts, which are connected to a resistor R2 of 2.2K, which is also connected to a resistor R1 560 ohms, and it is connected to ground like this. Let's call the output VO, the output, and the output will be V in multiplied, this is the formula for the voltage divider, R1 plus R2, 5 value of one resistor plus the value of the other resistor, and if you do your computations, you'll see that this gives us 1 volt. Let's have a look now to the non-inverting input of the op-amp. The configuration that we have is like this. We have all these resistors which are connected to each of our inputs, like the PSG, the PPI, and the 2 cartridges. So our configuration looks like this. We have our resistors, 4 of them, the inputs, which are tied together, and they go to the non-inverting input of the op-amp. And here we have our feedback and other stuff. This configuration is called a summing amplifier, and then inverting summing amplifier. So we'll see how it works. Our goal is to know which is the voltage in here. Is the output VO. We know that here we have 1 volt because of the voltage divider with these resistors, and in here we have the input of the different sources of sound, the PSG, PPI, and the cartridges, which are tied together, and they go to the non-inverting input of the op-amp. For each of the inputs, we have a current that goes through its resistor, different resistors and different currents for V1, V2, V3, and V4. We know that here we have 1 volt, and because of the way the op-amp works, we have also 1 volt in here. So all these currents are summed and go to here, and here we have a very high impedance, so the sum of these currents will go through this resistor and this gap. And we can write our equation as follows: V1 minus 1 divided by its resistor, the 4.7K, plus the same V2 minus V1, the resistor is 22K, plus V3 minus 1, resistor is 4.7K, plus V4 minus 1, and its resistor is 2.2K. This is equal because all these currents are tied together, they are summed, and they go through this resistor. For the moment, forget about this capacitor. We are not yet analyzing the frequency response, so let's assume that it doesn't exist and all the current go through this resistor. So we have here our output VO, and we have 1 volt which comes from here, so it is copied here. So the equation would be like VO minus 1 divided by its resistor, which is of, I don't see it, 4.7K. This is our equation. To simplify things a bit, let's assume that we have K of these inputs and the resistors are all the same. So our equation would be something like K, the input, let's assume it's always the same, minus 1, and let's pick one of the resistors, the one of the PSG, for example. These K currents should be equal to the current in the other resistor, 1 minus VO, divided by its resistor R4. Now, if you do your math, I'm not going to develop everything in here, you should arrive to something like VO equals 1 plus R4K divided by R48 minus R4K R48 VI. Listen here, it's a constant. I'm not interested in the constant at this moment. I'm just interested in the proportionality between VO and VI. And we can see that VO divided by VI, it is proportional to this quantity, which is minus R4K R48, which is minus 4.7K 2.2K, which is approx minus 0.5K. So we can see in the end this amplifier is taking the inputs, it's summing them, is dividing them by 2, and it's inverting them. That's okay for the PSG. We know that the PSG, the output from the engine, generates a signal which is like this. It's a 1 volt peak to peak, 1 volt peak. So it's like 0.5 here and minus 0.5 here. This will be turned into something smaller, which would be like 0.5 volts peak to peak, and this is within the specs of your SCART connector. But we know that the circuit is adding all the other inputs, so what happens with them, I haven't tried, but I would expect that it saturates if all of them are at the maximum level. And by the way, I haven't forgotten about our friend capacitor C16, so let's go for it. You can think about a capacitor as a variable resistor whose impedance goes down with the frequency. If you remember, in the calculations we did, we found that the gain of this amplifier was proportional to resistor HR4. Now the difference is that we have our capacitor, which is connected in parallel with the resistor, and we know that the impedance of the capacitor will go down as the frequency increases. If the impedance of the capacitor goes down because the frequency increases, the impedance of the two in parallel will also go down, and the gain of our amplifier will also go down with the frequency. Something that you can do is to simulate this circuit with KiCad. This is what I did in here, so I added the op-amp with the power it needs. I added the two resistors of the voltage divider. Here we have the feedback impedances, and this is a DC source which represents the PSG or any other entry, and we will configure it to generate frequencies between 0 and 22 kHz. Finally, I have here my output, and I'm using a large resistor to simulate a load. And this is the nice plot that we obtain with KiCad when we do our DC scan. In the horizontal axis we have our frequencies in a logarithmic scale, and in the vertical we have the gain in also logarithmic scale in dBs. So as you can see, for low frequencies it's multiplying the signal by 2 or 6 dBs, and as we approximate 1 kHz it starts to go down. Around 3 kHz, the power of the output is more or less the same as the input, and after that 3 kHz it starts attenuating your signal. And it makes sense, most probably all you have in this area is just noise, and you don't want noise in your music. And I think that's all for this low pass filter in your MSX, and I hope it was not very boring. Thank you very much for watching, see you in the next video, bye bye!